Hey everyone, we're going to be looking at target 7.3. I'm going to be talking about what you need to do to show me evidence that you understand this stuff. We are going to be going through an example of what an assignment will look like. I'm going to be trying to explain this as well as I possibly can. I'll be trying to point out exactly what you would want to show me. Um, Hopefully you did watch the video that I posted along with this. If you haven't done so yet, watch that one first because we are going to need that. If you've watched the video, what you saw was that we had these two white powders. Let me zoom in here a little bit. And that these two white powders were mixed together, and they started off at room temperature. So we'll just go ahead and write that right here. Sorry. They started off at room temperature. And then we let the reaction go. We mixed them together, and they mixed together and they actually turned into a liquid, which is kind of funny, but that's fine. And now that they've turned into a liquid, they're actually at negative 20 degrees Celsius. So the temperature dropped quite a bit. In fact, we know that it freezes to the board if you've watched the video. So this is definitely all of a sudden got really, really, really cold. So target 7.3 is all about trying to figure out why. So we're going to go through this example, and I'm going to point out the things that I would want to hear from you, the things that I want to be able to see. So this is kind of an interesting reaction. Let's go ahead and take a couple of minutes to go through it and really examine it. Specifically, what we'll be using is, well, the same thing we did last time we wanted to take track of energy. We drew an LOL diagram. So let's draw one. Oops. So, are you going to let me do a small L? No. There we go. So, L, and then O. Probably should have had this thing prepared. Oops. And we'll just copy and paste that. Oops. Sorry, I'm still figuring out all this stuff right here. And one more little circle. Probably should just drawn that from scratch. All right. So here we have our LOL diagram, and let's just think about what happened. So remember, this started off at room temperature and then ended up very cold. So how would we draw that on here? I mean, we've done stuff like that. We know that the energy the experience we have of temperature is energy that we've said being stored thermally. So we start off with a relatively normal amount of energy stored thermally. I'll just go ahead and put two little boxes here. Sorry, it's easier for me to draw circles. And we end up, actually start off with more boxes, because we'll start off here with 5 boxes, and we'll end up down here. We seem to have lost a lot of our energy that was being stored thermally. It got really, really, really cold. Oh, I don't want to do that over there. Sorry, we wanted to do this over. Oh, come on. Sorry, we wanted to do this over here. And I'm not too happy with using circles for these, but say love you. So we know that we started off with a lot more energy stored thermally. We end up with a lot less energy stored thermally. And usually the way we'd get around this is we'd say, oh, those other pieces of energy must have left the system. But the problem is we've seen that before, where energy leaves the system. That's what happens when things get hot, right? If you take boiling water and you let it sit on a countertop, it cools down because energy leaves the system. That's not what's happening here. And we know that's not what's happening here because if I put my hand near the boiling water, what do I feel? I feel energy going into my hand. That's not what we feel here. we do not feel energy leaving the system. We know that no energy here is leaving this system like this. That can't be happening. So if the energy is not leaving the system, where's it going? So let's examine that for a second. First, I want to draw out the particle picture for this reaction. Let's turn off this guy so we can see a little bit. We'll draw out the particle picture for this reaction. We'll get rid of this so we can just see a little bit better. And let's go ahead and take a look right here. So this is the reaction that's actually in the video. This thing right here is the barium hydroxide, BaOH2. And this is the ammonium chloride, NH4Cl. And then when it rearranges itself, it turns into barium chloride, BaCl2, and ammonium hydroxide, NH4OH. There's two of them. I mean, we might as well just go through and balance it real fast. We need two of those. So hopefully this looks nice and familiar. It's nothing too crazy. You've all done that before. But that's actually not the important part here. What we need to think about is what is going on here that could be taking energy that was stored thermally. Where could that energy have gone? Well, look at this reaction. Let's look at what's happening. We start off with the barium attached to the hydroxide, but we had to rip that hydroxide off. We started off with the chlorine attached to the ammonium, but we had to rip that chlorine off. Now, we did reattach everything, but we reattached things in a different way. There seems to have been a process of breaking these particles apart and recombining them. And somehow breaking all these atoms apart and then recombining them seems to have stored energy. So let's take a moment and let's think about what's actually happening here. See if we can narrow this down. So let's just think about three atoms. These atoms right here, we would say that these two are bonded. Let's draw a new layer on top of this. Sorry, the pain of using sophisticated technology means I have to learn how to use it. All right, so we would say that these two are bonded. Right, these two atoms are stuck together. We've already talked about how they must be sharing electrons in their valence layer. This also could be an ionic bond. That would work too. We talked about a lot about what bonding means back in Unit 6. This one right here is not bonded. Now, these two are attracted to each other. And if we want to break them apart, all right, if we want to break this bond, well, it's kind of like, I don't know, like magnets. If you want to separate two magnets, you have to pull them apart. And that takes energy. So we've broken the bond. And this took energy. This stored energy. Somehow separating these two seems to be a way of storing energy. That could be what's happening here. This energy that used to be going to making the particles move around, maybe now that energy is going into separate the particles. So now we can also recombine them and make new bonds. Look, here's a new bond. And just in the same way that if you'd want to take magnets apart, you have to put energy in. Well, what happens when you let the magnets go back together? They can release that energy. So here is what we are going to say, is when we break these bonds, when we pull atoms apart, we know that this stores energy. We are going to say that this energy is being stored by the arrangement of these atoms, by the fact that we've broken these atoms and pulled them apart. we will call this energy storage system ECH, or energy stored chemically. Now, when we want to release that energy that was stored chemically, we put the atoms back together. So in this reaction right here, we see a little bit of both. We must have torn apart some of these molecules, which we know stores energy, but then we have to recombine them over here, which we know releases energy. And there's no way to tell what's bigger, the energy stored, which makes ECH get bigger as these things get ripped apart, or the energy released as ECH gets smaller and these things are recombined. We can't tell without really examining the rest of the process. So let's go back and look at this. And here's what we're going to imagine now, that there must be some other way of storing energy, and this other way of storing energy relies on taking apart the atoms and then recombining them back in different ways. Well, specifically, let's name this. This is the energy before the reaction, and this is the energy after the reaction. So let's think about this. We must have had some energy stored chemically here. But then this 4 units of energy that I lost, they're still there somewhere. But what we think has happened is we've used that energy to pull the atoms apart. So I'm going to show that that energy that was stored thermally is now going to be stored chemically, which means we no longer have just 2 units of energy here. We have 6. We now have a lot more energy stored chemically. Apparently, when the amount of energy it takes to rip all these apart is pretty big. And yeah, sure, we get some energy back out when we put these back together, but it's not much. And we know that because this thing got really cold. It must have used that energy that used to be making this warm. Now it's using that energy just to have the atoms ripped off. All right, so next question. Will this stay cold forever? Well, the answer is no. Let's think about this later. Like 20 minutes, a day, a year later, some other time later. It's not going to be cold forever, right? Well, why not? Because energy is going to start making its way into the system. And it's eventually going to get back up to room temperature. And if we said here room temperature was 5 boxes, I think it's going to go back up to 5 boxes. So I have to put more energy in. So it's just going to pick up energy from the surroundings just because it's sitting there, just like we said back in unit 2, or excuse me, 3. So the energy stored thermally is going to go back up. But the energy stored chemically, well, that only changes when we rearrange these atoms. And we're done. There's no more reaction. So if there's no new reaction, that means that we didn't change this. We haven't rearranged any atoms. So ECH should be the same. So our energy stored chemically, when we ripped these atoms apart, it took a bunch of energy that was being stored thermally and now is storing it chemically. We will eventually refill this thermal account with energy from the surroundings. But from start to finish, we have so much more energy than when we started. Do you see how we have more energy than when we started? 4 whole units of energy entered our system here. We have a name for this. We say that this is an endothermic process. Endo means in, and thermo means energy. So energy enters, or energy goes in. There is also the opposite, which is energy. I gotta zoom in so I can actually write legibly. There is one where energy goes out. This is exothermic. So an exothermic process or an exothermic reaction is something where energy goes out. What I expect you to be able to do here is this. I expect you to be able to make an LOL diagram that tracks the energy stored thermally in a reaction and after the reaction. I expect you to be able then to figure out what must have happened to the energy stored chemically. Should it have gone up? Should it have gone down? I expect you to be able to describe things as either endothermic or exothermic. And then finally, and here's one more thing. So here's our reaction, right? I don't have the actual formula here. I probably should. So let me rewrite that again really fast. All right, so barium hydroxide. I'm not going to worry about states right now. I know I'm failing my own target. I apologize. Ammonium chloride, barium chloride, and let's turn off this thing so I can see a bit better. Oh, where are you? Come on. Sorry, I'm really just trying to erase that 20, and I can't figure out what layer it's on. Right? Streamer problems. I'm not a streamer. I wish. One of these days, guys. I'm going to become a full-on, I don't know, what game should I play to be really funny? They killed Club Penguin, so I can't do that. Barium chloride and ammonium hydroxide. All right, so this is the reaction that happened. But in order to get this reaction to happen, let's look what we're saying here. We had to put energy into the system. We must have put energy into the system to get this reaction to happen. So in a way, this energy is another reactant. So I will actually expect you to tell me that we had to put energy in along with the barium hydroxide and the ammonium chloride to get this reaction to happen. Energy here is acting like a reactant. Oh boy. So a bit of a long rambling video. I'm sorry. Hopefully it'll become a little bit more focused as we do more of these assessments. This was just a first introduction, so I sort of tried to talk about everything. But I expect you to be able to look at a reaction, describe it as endothermic or exothermic, to give me an LOL diagram that's reasonable, that describes what happens during or after, even before a reaction. I'll give you stipulations on that. And then to be able to describe to me how we're using energy, whether energy is a reactant in the reaction as it is in this one, or if energy is a product. Is energy leaving the system? Are we getting energy out that used to be hidden in the chemicals? By the way, this energy is still here. It's just stored in here. The energy is still in those products. It's just inside the bonds of those, or not inside the bonds of those products. It's in the arrangement of those products. We could actually get that energy back if we knew what we were doing. All right, everyone. I'll stop now. Please go ahead. Let me know if you have any questions. I will probably post our first evidence assignment for this tomorrow. Again, it is totally fine if you do not know how to do this first evidence assignment. I want to see what you can do. I'll give you as many tips back. I'll give you my key. And hopefully by doing this 2, 3, 4 times, you'll learn how it works. You'll gather 3 pieces of evidence, and then we can call it good. All right, everyone. Have yourselves a great day. Let me know if you need anything.